Hello everyone. We're going to be solving one more problem on the idea of moments about a point. And in this problem also, I will use both the approaches, the scalar and the vector approaches to solve for the final answer. Okay, so here is the problem. I first of all have the XYZ coordinate frame as drawn. Okay, so here is the z-axis, the x-axis and the y-axis in a minute. Okay, so let me label this as the x-axis, this is the y-axis, and this is the z-axis. Now on this I have an L-shaped body. It's some kind of a pipe. It's not necessarily an L, I guess. I should take my words back. Okay, so this is the entire body which I'm going to be drawing. Okay, and let me reduce it up till here. Okay, and this also protrudes down. Okay, so let me call this body as a O, A, and then the other point, I'll call this point as B, and then this point I'm going to be calling as the point C. Okay, so O, A, B, C is some bent bar. Okay, bent beam. Okay, and there are several couple of forces acting on it. First of all, what I'm going to do is I'm going to draw a set of dotted lines to show you what's happening here. Okay, there is a force acting at the point B, and let me draw this line as parallel to the y axis. So it's not necessarily parallel, so let me make it parallel first and then paste it again here. Okay, and let me make sure that this is parallel and drawn parallel to the x-axis. All right, so these are dotted lines, okay, which tells me that there is a force that is existing, and there is some information regarding that force that is given to me. So there is a force of magnitude, let's call this magnitude as F1. Okay, so this is a force F1 whose magnitude is 200 newtons. Okay, and there is a nice slope triangle given to us for this problem here. Once again, if you see a triangle, it's going to be a hypotenuse right angle triangle. So the hypotenuse is 5, then the opposite side is 4 in this, and then this is 3. Okay, so this is a force which is acting on the xy plane. Okay, so that's something that is obvious from the problem. Then there is another force that is given to me here. I'm going to extend this C fellow down a little more. Okay, and there is another force given to me. A very interesting set of axes are also drawn further here. Okay, so I'm going to be given a pair of axes which are absolutely parallel to the set of axes that I already have. Okay, the x and the y and the z directions. Of course, I'll just ensure that that is indeed the case. And I have another force, excuse me, which is drawn here, which is the force F2. Okay, so this force is a force F2 whose magnitude is 350 newtons. Okay, and then I'm given angles for this force. Watch this. From the tail of this force, I'm going to draw these angles in maybe the magenta or the purple color. From the tail of this force all the way to this vertical line here, which is essentially parallel to the z direction, I'm given the angle to be 120 degrees. Okay, which you can recognize as the coordinate direction angle, right? Then from the tail to the direction parallel to the y-axis, that angle is given to me as 60 degrees. And in this case, I'm given the third angle, so there is not much for me to do. Otherwise, I can make use of the cos square alpha, beta, and gamma to calculate the third angle. So this is given to me as 45 degrees. Okay, so which essentially tells me that these angles are the coordinate direction angles. Okay, and distances are also given from O to A. The distance is 3 meters. Okay, from A to B, the distance is 3 meters as well. And from B to C, the height is given to me as 2 meters. Okay, so maybe let me draw the height here. So these are parallel lines, and let me draw that as a vertical line. Okay, so this distance here is given to me as 2 meters. And as I typically do, I draw distances in dotted lines. Okay, what am I supposed to do? I need to find the resultant moment about the point O using the scalar approach, using the vector approach. Okay, so obtain the resultant moment about O due to the forces F1 and F2. Okay, use the vector approach, which means that you're going to be using the cross product, and then use the scalar approach. Which means that you'll be using the right hand rule. Okay, and I'm going to make use of the vector approach first because that's what I've been asked to do first. Okay, so the other thing we got to do is recognize from the problem. Okay, so this is first obtained. Okay, using the vector approach, which is essentially the cross product. Okay, and using the scalar approach, which means that I have to contort my right hand to do my bidding. Okay, so from the problem, it is obvious from given information, it is obvious that the force F1 is on the XY plane. Okay, that you can see is on the XY plane. Okay, and then the other thing is that the angles given are the coordinate direction angles for the force F2. Okay, for force F2, the angles given are the coordinate direction angles. Okay, and so alpha F2, beta F2, and gamma F2 are given to us as 120 degrees, 60 degrees, and 45 degrees, as you can see from the figure here. Okay, now I'm going to use the vector approach first. Okay, in the vector approach, I'm not going to redraw the figure. The first step is I write the forces as a vector. Okay, so if I write the forces as a vector, maybe let me do this very quickly. Okay, if I take this force F1, let me copy this figure. I think I might need to copy this figure. I guess I just destroyed my figure here. So somehow I need to copy the entirety of this creature, which I'm trying to do. All right, I think I got it. Yeah, that's better. Okay, so this is the z-axis, of course. The first thing I got to do is I got to take this force F1 and break it up into its components, which I'm going to do right here. Okay, so I'm going to have a component starting from the point of application, which is coming out here. Let me draw that as aligned with this line here. Okay, so that's one component of F1, and then the other component of F1 is going to be pointing in this particular direction. Okay, so this is the point of application of the force F1. So this is going to be 3/5 F1 along the y direction, and this is going to be 4/5 F1 along the negative x direction. Okay, so my first step is to write these forces as vectors. Okay, write the forces F1 and F2 as Cartesian vectors. So the force F1 is easy. Okay, it's an XY force, so there is no Z component to it. So this is going to be minus 4/5 F1 in the I, as you can see, plus 3/5 F1 in the J, plus 0K. Okay, and then if I do the simplifications, the magnitude of F1 is known to me. Okay, so this tells me that the force F1 is going to be minus 160I, and then 120J positive, and 0K if you want, so many newtons. Okay, then likewise, so this is the force F1. Then I come to the force F2. As you can see, I'm still looking at the same figure for the force F2. This is going to be F2 cosine alpha 2 Okay, it's cosine alpha f2 I, f2 cosine beta f2 j, f2 cosine gamma f2 k. Okay, these are all given to us. Alpha f2, beta f2 and gamma f2 are known to us, as you can see from the figure. Okay, so this tells me that f1 or f2 is f2 times cosine 45, f2 times cosine 60, and then f2 times cosine of 120k. Or if I take these values and write them off, then the force F2 becomes the following: 248I and 175J and negative 175K, so many newtons. All right, fantastic. What's my next step? My next step is to write the position vectors from the point of interest to the line of action of the forces. Okay, so that's my next step in black color. So write position vector from point of interest O to any point to the line of action of the force, to line of action of F1 and F2, where I am making use of the key idea, right? The key idea which I'm going to write here is MO resultant is MO due to the force F1, moment due to the force F2. Okay, so this is the key idea. All right, so I'm right at this figure here, so I can write the position vectors. So there are two position vectors that I have. One is from the point O to the point B. Okay, so that's going to be in the magenta color. So that's going to be to the line of action of the force F1. So this is going to be position vector R, OB. Okay, I'm going to have one more position vector. I'm going to move this point C right down here. Okay, and the point B, I'm going to move right down here. There is one more position vector that's going to be from the point O to the point C. Okay, which I'm going to draw this way, and I think that should be reasonable. Okay, so this position vector here is ROC. Okay, it's very important to realize that these position vectors are from the point of interest O to the line of action of the force. Okay, so what I can see here is that, okay, this position vector is ROB, which means I need the coordinates of O, B, C, and A, and they're easy to write. The coordinates of O are 0, 0, and 0 meters. The coordinates of the point B, okay, the point B is on the XY plane, distance of 3 meters each, so 3, 3, and 0, and then the point C is 3, 3, and then minus 2, because it's on the negative Z direction. Okay, then once I have that, I can write the position vectors. Okay, so this is ROB, coordinates of the last point minus the first point, so this is going to be 3I, 3J, 0K, so many meters. This is for the force F1, and then ROC, which I can write as 3I, 3J minus 2K meters. This is for the force F2. Okay, then once I have the position vector, all I have to do is do the cross product. This is so straightforward. The vector approach is very simple because there is not much intuition involved. When intuition starts coming into play, then the brain starts playing tricks on us. Okay, so, and it is important that you understand both the approaches, especially not just especially from the point of view of exams, where I might ask you to do one or the other, or I might ask you to do both. I think in the field as an engineer, you need to know how the right hand rule is causing a bending of, maybe, if you're an agricultural engineer, the wind is going to bend the tree. So what is the bending moment, and what is like a kind of a failure moment at the point where the tree is going to crack, or some kind of a practical problem of that nature. It's very important to understand what that is. Okay. So then my next step is to say that, okay, resultant moment, as you know, is moment about the point O due to F1, moment about O due to F2. If I use the cross product, it's always the position vector cross to the force, always the position vector cross to the force. And then all I have to do is for each of these cross products, I set up my determinants. So I, j, and k. That's the first row. Then the second row is filled by the elements of the position vector. The third row is filled by the elements of the force. And then I have to add this with the other cross product, which is I, j, and k. Okay, and the second row is given by the elements of the position vector, ROC. And then this is going to be 248, 175, and minus 175. Okay, and if I do the cross products, this first determinant is going to give me the following cross product, and I will be posting a document on how to do determinants and so on, and I'm pretty sure that most of you have done it before, so this is not a surprising thing, hopefully. That's the determinant from there for the first one, and then the second one is going to give me 175i, 29j, and then 219k. Okay, which essentially tells me that the resultant moment is going to be the vector sum of these two, obviously, right? So that's going to be minus 175i, then 0 plus 29, so that's 29j, and then 840 minus 219, which is plus 621k, so many Newton meters. So this is the Cartesian form of the resultant moment vector, of the resultant moment vector. And of course you can calculate its magnitude as the square root of the sum of the squares. 175 square, 29 square, 624 square to the power 1 by 2, which is going to give you the magnitude. Okay, so many Newton meters is the magnitude. I don't have the number in front of me, but you can fill up the details. Okay, now I go to a much more elaborate procedure. This is a scalar approach. Okay, I'm going to go to the new page here. Vector approach, basic idea was that I started off by writing the forces as a vector. Then I write the position vector for each force from the point of interest to the line of action of the force. So always from the point of interest, and to the line of action of the forces. And then I do the cross product, I go on my merry way, and that's about it, right? Then I go to the next approach, which is the scalar approach. This is a little more elaborate. Okay, it is nicer in my opinion. Okay, in the scalar approach, the basic idea remains the same. Okay, so basic idea remains the same. The resultant moment is the vector sum of F1 and F2. Okay, there is nothing here. So here is what I'm going to do. I'm going to take each of these forces separately. Okay, so first consider moment about O due to F1. So my idea is, okay, how do I find this using the scalar approach? And I'm going to bring back my figure, okay, from above. And I may have to do some cleanup act on this figure. I think I might just take this much cleaner version of this figure. I'm interested only in the force F1 for the time being, so I'm not interested in the rest of the details. Okay, so I'm just going to copy that and bring that big guy here. Okay, so this is my force. I don't need any of these pesky characters. I'm going to get rid of it. And I immediately know that, okay, hey, this force has components in the x and the y direction, right? So I'm going to say, okay, this is the component along the x direction, which we know. This is the component along the y direction, which I know. Okay, so this is going to be 3/5 F1, and this is going to be 4/5 F1, as you know from before. So I'm going to get rid of this slope triangle and all that kind of stuff, because that's just an unnecessary distraction for me. Okay, now this force, as you can see, is on the xy plane, which means that there is no z distance between this force and along the z-axis. Okay, so this force is not at a z distance of 0. Okay, so for the point B, this is something that you want to notice. So point B is the point of application of the force F1, which means that B is at a distance of 0 from the along the z-axis. Okay, so it's a point on the xy plane. Okay, which tells me an important thing. If I have to find the moment of these two forces, then I can do the following. Okay, moment about O due to F1 is going to be moment about O due to the 3/5 F1, moment about O due to the 4/5 F1, right? And what is the moment about the force about the point O due to the 3/5 F1? You got to be very, very careful. Okay, first thing is, okay, I look at the line of action. From the point O, I draw a line parallel to that force, and then I find out, okay, hey, the perpendicular distance between these two is going to be a distance of 3 meters. Okay, that's the perpendicular distance. Okay, then I say, okay, I'll start off by writing it this way. So this is going to be 3/5 times F1 times the distance of 3 meters. What is the direction? Use the right hand rule. If I use the right hand rule, my fingers aligned with the force 3/5 F1, my palm is facing the point O. You have to realize that your right hand fingers are now going to be parallel to the y direction when you do that. And if I curl my fingers, my thumb is going to point in the z direction. Okay, so this is going to be producing a moment in the positive z direction. I do the same thing for the 4/5 F1 from the point O, so let me take a different color here. From the point O, I draw a line parallel to that force. I take this force and I extend its line of action right here. Okay, and you'll see that, okay, hey, this distance is known to me. Right? That distance is given to me as 3 meters. And that's a perpendicular distance, right? Which means that the moment due to that force is now going to be the following. It's going to be 4/5 F1 times a distance of 3 meters as well. Okay, what is the direction? You've got to be very, very careful once again. Fingers aligned with the force. Your palm faces the point O, so in this case your palm is going to be parallel to the x-axis. Okay, very important thing. As your fingers are going to be parallel to the x-axis for the force 4/5 F1. You curl your fingers, thumb is going to be pointing along the z direction. Okay, so this is also going to be in the k direction. So this can be obtained. So this is moment about the point O due to the force F1. Okay, and I can do the addition of these terms. So let me do that very quickly. So this is going to be 3/5 F1, which was given to us, if I remember right, as approximately 200 newtons. So this is going to be 3/5 times 200 times 3 in the k plus 4/5 times 200 times 3 in the k, which tells me that moment about the point O due to the force F1 is going to be approximately 840 k. Okay, Newton meters. So we're done with one of these forces. And we got to do the same thing with the other force as well. I mean, there is not much of a problem at all. Okay, now I'll go to the next force. Okay, so consider moment about O due to the force F2. Now this is a slightly tricky customer. Okay, you got to be careful here. F2, remember or recall, F2, which I'm going to write as F2xi, F2yj, F2zk. Okay, this was written out as the following. Okay, 248i 175j minus 175k, so many newtons, which tells me that F2x is equal to 248 newtons, F2y is 175 newtons, F2z is minus 175 newtons, which means that F2x is along positive x, this is along positive y, and negative Fz is along positive z, so which means that F2z is going to be, which is equal to 175 newtons, is along negative z. Okay, so this is the first thing I typically do. Okay, and then I say, okay, if I'm doing the moment of these forces, then moment due to the force F2 is going to be moment about O due to force Fx2, moment about O due to the force Fy2, moment about O due to the force Fz2. Okay, this is the next step in the problem. Then what do I do after this? I go back and bring my figure. Excuse me. Now I need my figure with the other forces present, but I guess I don't need that. I'll just get a cleaner version of this figure here from here. Okay, and I'm going to get rid of some of these things which I'm not very interested in. Okay, so I'm going to get rid of all of these creatures. That is, not all of them, but some of them. I need the y-axis. I'm going to cut that off, and then I'm going to take this off as well. And probably I don't need them too. Okay. Then what I do is this. Okay, I start by looking at the force Fx2. Okay, look at the force Fx2. I'm going to draw it in this color here. So the force Fx2, as you know, is parallel to the x-axis. Okay, so this is the force Fx2. And to find the moment of this force about the point O, I can do a couple of things. Okay, here is what I can do. I can take this force Fx2, and without changing its direction, I can slide it all along to the y-axis and the z-axis. So I take the force and I slide it to the y-axis and the z-axis. Okay, you notice that this distance between the point B and the point C, where this force was acting, that was also given to us as 3 meters. Okay, so I take this force Fx2 and slide it to the y-axis. So here is what I do. Watch this very carefully. I take this force and I bring it down here. Okay, what I'm doing is I'm just sliding it along that line, but then I'm making it stick on the y-axis. And I guess if that is the situation, right, I have to bring it to where the point B is sitting. So I'm just going to bring it down there. Okay, so that's where the force Fx2 is for me. I have just translated it, which is completely fine. And then you'll notice that, okay, hey, this distance is given to me as 3 meters, which means that the moment of Fx2 about the point O is going to be Fx2 times 3. And if you use the right hand rule, this moment is going to be pointing along the negative z direction. Okay, so this is going to be Fx2 times 3. But we are not done yet, because I can take this force Fx2 and slide it parallel to the slide it along the z-axis as well. Watch this. You know, I can take the z-axis, I can extend it a little down here. Okay, and I can take this force Fx2, take this guy and bring him here. I guess let me write it this way, so that now I take this entire creature and I bring him here. And you can immediately see that, okay, hey, there is a perpendicular distance here too for this force. And what is the moment of this force? If you use the right hand rule, your fingers aligned with the direction of the force Fx2 as you are showing it here, your palm should be facing the point O, which means you're now sitting underneath the XY plane. And if you curl your fingers, the direction of your moment is going to be about the negative y-axis. Okay, so it's going to be about the negative y-axis. That is very important to understand. Okay, so this is going to be fx2 times a distance of 3 meters as well. Here, if I remember right, this was probably 2 meters. I'm sorry, I apologize for this error. That is 2 meters. So which means that this is a distance of 2 meters. So there's fx2 times 2. So many Newton meters. That's the direction of the moment. Okay, I hope this is clear to everybody, which means that I can now say moment about O due to fx2 is going to be nothing in the I, because it's a force parallel to the x-axis, so it's not going to cause a moment about that direction. It's going to be minus fx2 times 2 in the j, and then minus fx2 times 3 in the k. I'm sorry. Okay, so the force fx2 is parallel to the x-axis, which means that will not cause a moment about x direction, which is why this guy is 0. Okay, so I'm done with one of them. I got to do the same thing for the rest of them. Okay, so let's do this. And I'm going to copy my figure here from before. Okay, with your permission. I'm sorry I have to keep doing this many times, but that is the best way to solve these problems. So I'm now going to look at moment about O due to the force F2y. I think I call it as fx2. It's all f2x, so maybe I did call it as fx2, so that's I guess my naming mistake here. So let me call these as fx2, y2, and z2. Okay, so these guys are going to be different. I mean, they're the same thing. I know that you understand what I'm saying. I'm too late into the lecture to start off again, so I hope you don't mind that. So this is fx2, fy2j, and then fz2k. Okay, in that direction. And now I gotta go back and bring my figure again. Fantastic. What a day, right? Okay, look at this force here. Okay, we got to do the same kind of gymnastics for this force as well. I'm going to cut off some of these things. I don't like any of these guys, so I'm going to cut them off. Okay, I'm going to cut off that guy too, and I can cut that off. And here is the point C. Okay, and if you look at the force F2, fx2 and fxy and so on, so I got to maybe slightly change these guys as well. So maybe let me do that quickly too. Okay, just so that we are all on the same page. So this is fx2, fy2, fz2. So fy2 is 175 Newton, so that's along the positive y direction, right? So that's going to be drawn in the positive y direction. Okay, so this is going to be fy2, which is 175 newtons. And I do the exact same thing that I did before. I take this force, okay, and then I go and plop it, in a direction that is parallel to the y-axis this way. And you'll immediately see that, okay, hey, there is a perpendicular distance for this force starting from the line of action of the force all the way to where a line drawn parallel to the force comes from the point O, right? Which means that this is a perpendicular distance of 3 meters. I hope that makes sense. Which means that this is going to cause a moment, which is going to be in the z direction using the right hand rule. Okay, so this is going to be fy2 times a distance of 3 meters, and this is in the positive z direction. But don't forget, this fy2 is underneath the xy plane, which means that if I take this guy here, okay, I guess I shouldn't do that. If I take that guy and I extend him here, and I take this fy2 and I draw it there, is going to be slightly convoluted, so maybe I can do some adjustments and see what happens. Okay, let's see how to do this. I want to bring this force down here. I hope it's a little clear to everybody. Okay, and this is a perpendicular distance, and this distance is the same as the distance from B to C, so that's going to be 2 meters. And so you see that this force Fy2 is going to cause a moment about the x-axis if you use the right hand rule. Okay, so this is going to be Fy2 times the distance of 2 meters, positive direction. Okay, and so you recognize that if I write it as a moment about the point O due to Fy2 is going to be Fy2 times 2 in the I, 0j, as you would have recognized, this is a force parallel to the y direction, so it will not have a component of moment in the y direction. And then I'm going to have a positive contribution along the z direction, so Fy2 times 3. This is going to be so many newtons. Okay, so that's one thing that I have. Then I had previously this creature here, which is Fx2. I need to do one more thing, which is Fz2. Okay, so lastly, okay, look at moment due to Fz2. Okay, and for this too, I need to bring my figure. I think I have enough space for that, so let me scoot down and bring my figure from here. Okay, or maybe I can even reduce the size of that guy. I don't want to do that. I copy that, and we're almost done with this problem. I thank you for your patience. Okay, so here is the setup. Okay, I'm going to get rid of some of these terms here, get rid of all of these as well, and get rid of the entirety of that, and maybe get rid of that too. All right, and maybe let me look at Fz2. Okay, so I was told that Fz2, if you go back and look at it, Fz2 is 175 newtons, but along negative z. Okay, so that is what we were told about this particular force. So I'm going to bring that and write that down here. Okay, and then so my force is going to be directed along the negative z, so I'm going to be drawing it. This is the point of application, so the force is going to be directed this way. Okay, so this is going to be Fz2, and I'm going to be doing the exact same thing that I did previously. Okay, I'm just going to copy these two guys. Okay, I'm going to copy that and I'm going to paste it. I don't need that, so I'm going to take this and I'm going to bring that guy here. And now it is very easy for us to see that, okay, hey, if I join these two lines, okay, parallel lines, you see that this distance is 3 meters. If I use a right hand rule, this force is going to produce a moment about the positive y direction. Okay, if you use the right hand rule, Fz2 times a distance of 3 meters. Okay, that's going to be producing a moment about the positive y direction, so that's going to be Fz2 times a distance of 3 meters. And then likewise, you can also see that, okay, this is immediately recognizable, that if I draw a line here, that is also going to be at right angles. There was another right angle that was drawn there. That's going to be at right angles. This is the direction of the force, and this is going to be causing a moment about the negative x-axis. Okay, so this is going to be, if I use a right hand rule, this is going to be Fz2 times a distance of 3. Okay, I hope that is obvious to everybody here. Okay, so which means that, if I now look at Fz2 and I write it out as a vector, that's going to be moment about the point O due to Fz2 is going to be minus Fz2 times 3i. Then I'm going to have Fz2 times 3j, 0k. It is obviously clear that since the force is along the z direction, it will not have any component in that particular direction. Okay, which means that the total moment, okay, so I'm going to write this in the black color. So MO due to F2 is MO due to F2x, MO due to F2y, MO due to F to Z. Okay, and we have all of these. I'm just going to collect all of them and bring them down here. Okay, with your permission, I'm going to have this creature, which is the first of the lot. Okay, that's going to be brought down here. Okay, so this is MFX2. Then I'm going to have MFY2, which is this big guy here without the newtons. I can put the newtons later. Okay, that's that plus that, and then plus this last guy that we just did here. Okay, copy that and paste that there. Okay, and we are good to go. Okay, the important thing that you got to realize is that, okay, fx2 magnitudes was 248 newtons, fy2 was 175 newtons, fz2 is 175 newtons. The negative sign not used because we said fz2 is along negative z, and we already drew it that way. You see, we already drew it that way. Okay, so if I add up everything, right, and then I get MO due to F1 and F2 together. Okay, MO due to F2, if I do the substitutions and so on, I end up getting minus 175I plus 29J minus 219K. Previously I had MO due to F1. If you scoot back, it's 840K Newton meters. This is so many Newton meters. And what do you know? The resultant, which is due to F1 and due to F2, is the same thing. If I do the addition, I'm going to end up getting it as minus 175I, and then that's going to be 29J, and then plus 621K. So many Newton meters. And important point, the same answer, okay, as in the vector approach. I hope this made a lot of sense to all of you. Once again, practice. Okay, please practice the right hand rule. It is a lifesaver. All right, I hope you're all staying safe. Take care of yourselves. Bye bye.